To integrate a function where the domain is of a general type, let's say it's not necessarily a rectangle but has any shape like this, well, the idea would be first try to classify this domain in a domain of type 1 or type 2 that are going to be described in this way. A domain is going to be of type 1 if we have that the x vary between two constants, a and b, and the y vary between two functions, g1 and g2. So when we have then a domain defined where the x vary between two constant values and the y vary between two functions, and these functions depend on the other variable. So in those cases, the double integral over this region is going to be calculated in this way. So first, we integrate the function with respect to the variable whose limits are given by two functions, and we leave for the end the variable x whose limits are just two numbers. So in this way, we're going to have that the limits of the outer integral will be always constants, and the limits of the inner integral, the one that we do first, are going to be in terms of the other variable. We're going to say that the domain is of type 2 in case that is defined by these limits here. So now is the y, the one that vary between two constants, and the x vary between two functions. So y vary between the numbers c and d, constants, and x vary between two functions, the functions h1 and h2. So when we have a domain given in this way, so now the outer integral is going to have to be the one of y, because it's the one that vary between two constants. So we do y then as the outer integral, and the interior one is going to be the one that depends on the two functions. These two types of domains of a function are not necessarily one or the other. Depending on the region, we can describe it as a region of type 1 or of type 2, and the same region may be described in two ways, as type 1 or type 2. So in those cases, we will have two different ways to calculate the same thing. For instance, let's calculate the double integral of this function over the region bounded by these two curves. Well, the first thing that we need to do is to identify the curve. I mean, we need to graph this to have an idea what the region is. So we write the two axes for the region, and we're going to draw the two functions. One is y equal square root of x, that is a function that looks like this, and the other one is y equal y cubed, so this will be y equals y cubed. And so this is then the region where we want to calculate the integral over. First, let's decide if this is a region of type 1 or type 2, and as I said before, it could be that it's both. So for instance, where of type 1, we have to define this region as a variation of x, or in this case is correct. We can define this region as x vary between two constants, 0 and 1. And we can define the variation of y as vary between two functions, right? So the variation of the y, a generic one here, will be vary between this function and this function. So it will vary between x cubed under and on top square root of x. So we were able actually to describe this region as a region of type 1. So we can calculate this integral now as an integral of type 1. That will mean that we are going to put as the outer integral the one of the variation of x. So this is going to be dx. And inside here, we are going to put the integral between the variations of the functions. That will be between x cubed and the square root of x dy, right? Is the y the one that is very between these two functions. And in here, we will write just the function that we want to integrate, that in this case will be 4xy minus y cubed. And then we start by doing the inner integral. So we leave the outside one outside, and we are going to work just in the primitive of this function. Remember that this function here is a function of y, meaning that x is constant. So we are going to do the integral taking into account that. So that will be 4x, that is a constant, goes out, y squared over 2 minus y4 over 4. So this is the primitive of this function, and now we have to evaluate between this and this, between x cubed and square root of x. So now we do the evaluation, always keeping outside the integral between 0 and 1 dx. And in here we are going to do the evaluation. And when you do the evaluation, remember that the variable was y. So we are going to be substituting only when there is a y there. So we can do a simplification here. 4 divided by 2. Let's just put there. Okay, so now let's plug in square root of x in everywhere where there was a y. So then we're going to have here 2x times x minus, and now square root of x to the fourth power is x squared divided by 4. That is the evaluation at square root of x. So now we're going to put minus and do the evaluation at x cubed. So the evaluation at x cubed is going to be 2x times x to the 6th power and then minus x to the 12th power divided by 4. Okay, so the result of this subtraction will be our next integrand. And so this is the integral between 0 and 1. And we do the operations here. The result is 2x squared minus x squared over 4 minus 2x to the 7 and plus x 12 over 4 dx. Okay, so the next step is, well, we can still combine some like terms there before doing the integration. Let's combine these like terms and then do the integral. Combining like terms, that is the integral, that it comes from here, and then we just integrate here. The integral of this will be x to the 13th power divided by 13 multiplied by 4, and then minus 2x8 to the divided by 8, and so plus 7x cubed over 3 times 4, which is 12. And this is going to be evaluated between 0 and 1. Let's evaluate now. Evaluated at 1 will be 1 over 52 minus 1, 4 plus 7, 12 minus 0. So this is common denominator 156 and then 55. Okay, so this is then the value of the double integral of these functions over these two curves. As I said before, this region, we decided to describe it as a region of type 1, but we could have described this one as a type 2. I'm going to set up this description to see how would it be to set up the same region, but now as a region of type 2. Now we need to look at this region from this direction. Let's say that we rotate this graph like this and try to see what would be the variation of x if we consider now that the y is vary between two constants, 0 and 1. So in that case, if we consider that y is the one that is vary between the constant 0 and 1, so x is vary between what? So that is where we should be looking from this direction, and we consider here a line like this is vary between this function and this function. So what function is that? Well, this function is x equal, putting the square root in the other side, y squared. So that will be the lower band. X is vary between this function and on top this other one. So what function is this one? Well, x is equal cubic root of y. So you see that already here the description looks a little more involved, but I'm going just to set up the integral, and I hope you continue to do the operations and check that by describing the domain in this way, you will do completely different operations, but you are supposed to get the same result, so be sure that that happens. So the setup of the integral now will be the integral between 0 and 1, and this is going to be now dy, right? So the outer variable is going to be y, and inside we're going to do the integral between this and this, y squared and cubic root of y, of what? Of the function 4xy minus y cubed, and the variable here is the x, right? The one that is vary between these two. This will be the setup of the integral if we consider this domain as a domain of type 2. And you can calculate these integrals in the same way. So you leave this for the end, so that will be the dy integral, and we need to do the primitive of this. Remember now the function is a function respect to x, so then the primitive is going to be 4y x squared over 2 minus the primitive of this respect to x is going to be y cubed, that is just a constant, x. And this should be evaluated between y squared and cubic root of y. And so continue the operations here. So certainly here we have a 2 there, and so this will be the integral between 0 and 1 of 2y x squared minus y cubed x evaluated between y squared and cubic root of y dy. So be sure that you do these evaluations now. I mean, I'm leaving this problem like this. The remaining steps is to evaluate this expression at here minus at here. When you are done with that, calculate the primitive respect to y and evaluate between 0 and 1. When you do all these evaluations, the final result, as you know, because you just calculated before, should be 55 over 156. Even though the double integral is associated mostly with the volume, we can associate it also with an area by just calculating the double integral of the function 1. I mean, the function that we are going to calculate the volume under is just a function constant equals to 1. And so the result of the double integral will be just the area of the region over which you are integrating. So for instance, let's calculate the area enclosed by these two curves. So if we draw these curves, one is the familiar parabola x squared, y equal x squared, and the other one is y equal x cubed. And we want to calculate the area under these two. So you should be able to do this problem as an integral of a function of one variable, but can be done also as a double integral by considering just a one as a function to integrate. So let's write down how would be the integral for this case. This is the region R, so let's decide if it's type 1 or type 2. So let's say that if we consider the variation of x between 0 and 1, so we have the description as this region vary between 0 and 1, and then the variation of y, if we consider here a vertical line, will vary between this function and this function. The y will vary between the blue function, which is x cubed, and the other function, which is x squared. So to calculate the area of the region will be then to calculate the double integral of just 1 dx dy. So in this case, describing the domain as a domain of type 1, so we are going to calculate this integral as the integral between 0 and 1 dx, right? So the x will be the outer integral, and inside we are going to put the integral between this and this function, x cubed and x squared, of just the function equal to 1 dy. And so now we calculate, as before, the inner integral first. The integral of 1 is going to be just y, evaluated between x cubed and x squared. So we do this evaluation now. So evaluating here will be x squared minus x cubed dx. And now we just integrate this function of one variable. So then that will be x cubed over 3 minus x4 over 4 evaluated between 0 and 1. That will be just 1/3 minus 1/4 minus 0, which is 4 minus 3, which is 1 over 12. Then this is the value then of the area of this region. So this area here measures 1 over 12 units. In general, we can say that the double integral of a function over a region, if the function is positive in the region, will coincide with the volume under the surface over the region R. For example, let's find the volume under this surface over the region bounded by these curves here. Let's first picture the region. So if this is the x and y axis, this region goes from y equal x, which is the line at 45 degrees, and x equals 1, which is a vertical line like this. So the region is this region determined between these three curves. Let's calculate the volume under this surface over this region. Since this function is always positive, we can define then the volume as the double integral over this region of this function. And let's see how do we describe this. In this case, as x varying between 0 and 1, and y, we consider here a segment of y, will vary between this lower function, the blue one, which is y equals 0, and the orange function, which is y equals x. And so we can calculate this function by calculating the integral between 0 and 1 of the integral between 0 and x of a square root of 1 minus x squared dy and then dx. And this is the integral between 0 and 1 of let's calculate the primitive of this. Observe that this function doesn't depend on y, and we are integrating respect to y. So then this is going to be a constant that goes out, root of 1 minus x squared y. And then this we are going to evaluate between 0 and x. So that will be the integral between 0 and 1. And so we evaluate now. Remember that the variable is the y. So this will be then 1 minus x squared x minus 0 dx. So the function that we have to integrate, 0 and 1, is x square root of 1 minus x squared dx. So this function is not going to be, it's not in the table, so we need to do a change of variable. So let's calculate that separately. So I'm going to separately calculate just the primitive of a square root of 1 minus x squared dx. So to calculate the primitive of this, I'm going to do a change of variable. 1 minus x squared equal u. The derivative is minus 2x dx equal du. And so the dx is du over minus 2x. We have du, we had the x, and we had the change. So we come back to the integral, and the integral will be x square root of just u times dx, which is this, will be du over minus 2x. X and x cancel, and so this is the integral of minus 1/2 square root of u du. So we integrate this square root of u, that will be minus 1/2 u to the 3/2 divided by 3/2. Now the two cancel, and the result of this is minus square root of u cubed divided by 3. And now I'm doing the change of variable, so this is minus square root of 1 minus x squared cubed divided by 3. So we have that the primitive of this function is this function, a function that started with x and finishes with x. U was just an intermediate variable that doesn't need to be involved with the change of extremes here. So by now knowing the primitive, we are going to come back here and just evaluate. So the integral between 0 and 1 of x square root of 1 minus x squared dx is just this primitive that we just calculate, minus square root of 1 minus x squared cubed over 3 evaluated between 0 and 1. And doing the evaluation, this is minus 0 plus 1/3, which is 1/3. So we got that the volume under this surface over this region is equal to 1/3 units.